In a world where slides are life, one man stands on the cusp of a life-changing choice. Big slide or small slide, or both.
Today the unthinkable happens. We're going to be using multiple resistors in a single circuit. Just wait until we get to multiple power sources in a single circuit. We won't be doing that, but multiple resistors, heck yeah, definitely. Now, for this explanation, I'll be using slides. And if these slides come out of nowhere, then backtrack a little bit and look at the video called Ohm's Slides, which is a weird name for a video. Just look at the video. It'll explain something that you're going to need for today. Now, let's just assume that these slides are like resistors, right? They have a voltage going over them, on them, and a current going through them. People going on the slide, and they have the resistance, right? The width of it. So we have a high resistor and a low resistance resistor. High resistance resistor, low resistance resistor. And now we need to be able to combine them. So we gotta do a fusion dance and figure out how many options we got. Two options.
So how do resistors behave when they are in parallel? Well, let's put two resistors in parallel, and you can see they have a different resistance because this one is thinner and this one is thicker. So this one has a higher resistance. It's harder to get as many people on this slide. So as you can see, if we have this amount of people, they're screws obviously, but if we have these people, well then we'll have, let's say, two go over this slide and probably something like four going off this slide. And as you can tell, I'm not very good at getting screws to go off of cardboard slides, and I dropped one on the floor. Let me get it real quick. Yeah, there we are. But there's actually a choice. So what you actually do in parallel is you just make a thicker slide, because you set them next to each other and people can choose, obviously, but they're going to go nice and in a balanced way, unlike real people. And you're basically making a thicker slide. Let's put them here, maybe. They'll fit better because of the cut. Yeah. So you're basically making a thicker slide, right? And so our voltage is the same on both slides. They have the same height. Now this one isn't made that well, but they have the same height right about. But the current is divided. So let's check that here. Parallel. Voltage is the same. Current is divided. And the circuit would look like that. Voltage is the same. Current is divided. And it prefers a lower resistance. So the current wants to go more over the lower resistance because there's more space than the higher resistance, right? So that makes sense. That's what parallel does. Now, what is series? Well, it's not quite like this. It's not, that doesn't really work, because then people would have to go down and up on this one again. Going up the stairs would kind of mean getting more energy for gravity. So that would mean you have to actually pass a voltage source, so a power source. So what it looks like, more like this, is like this. It is, let me just throw this away. Not going to need it anymore. It's going to be great if I have to do another take, then that slide's going to be all gone. Well, I'll have to either get some tape here, but this is what series looks like. So you can see the voltage is divided over the two because this one's only getting half of the height that it goes down. It doesn't go down all the way, it goes down half of the way. And this one goes the other half, right? So we have this total voltage of this height here, and it's being divided over 2 slides. Now, what about the current? Well, let's see if we're gonna actually get these to go all the way on it. That would be great. Oh man, amazing. The current is gonna go over both slides equally. So when we're using series, not parallel, here is, I'm making a mess. When we're using series, the current is the same because the same amount of electrons is going to go over the slide, but the voltage is divided because one of the slides needs to go halfway and the other needs to take the other half. So the voltage is divided. Now voltage is divided in favor of the higher resistance. So the smaller your slide, the higher the voltage because it has to push harder over that particular slide. If you have two different, oh, I did still need my smaller slide. Let me get it real quick. Oh, it's not broken yet. Great. So if we have this setup where we have the big boy, low resistance, and then the smaller, over this thing, this one, they have to push harder, right? So he gets a higher voltage, if that makes any sense. You don't see that reflected in the height here, sadly.
Now if you get confused by using these slides, then I don't blame you. It's a metaphor. It's a little weird here and there, and if it doesn't work for you, it doesn't work for you. I'm just trying to give you a visual cue for how to do the math with these things. But if you don't understand this, just go with the math. The math always works. Why does the math always work? Because math always works. Now let's look at the math of equivalent resistance, which in Dutch is called vervangingsweerstand, which then reverted back to English is called replacement resistance. And we call it that because you can replace a circuit or multiple resistors with one resistor. At least in value, mathematically you can do that. In an actual circuit you can usually not do that because it'd be weird if you could. But yeah, you can replace a whole circuit with a single resistance. And you can calculate that resistance, and it's useful to do that. Wow. It's useful to do that. So we can work in both parallel and series, and we can calculate the equivalent resistance of both. Now for both, there is a different equation, and this one is for series. It's relatively simple. I write RV because vervangingsweerstand, which is the same as equivalent. In English you would see REQ, and it's just, putting all the resistors together. It's just, using the plus sign. So that's relatively simple. I don't think I really need to, go over that in depth. If you are doing series, you can just do this. Easy. However, if we're doing parallel, it looks like this. Now, if we just ignore these one thingies and the division here, it looks, strikingly similar. It's just RV is R1 plus R2 plus R3, and then, on and on and on, as many resistors as you have. But now all of them are divided, or 1 divided by R. And it looks a little weird, right? But it really isn't that hard. But to explain why we're doing this is a little bit of a math trickery, and I'm going to do it with language. And, let's just get into it.
Why are we going to do that? Well, I'll tell you about a little trick we can do in math, and that is finding the opposite of what we have. So what we're doing is we are doing resistance, right? We're doing math with resistance. Now, if I just subtract our resistances, which would make sense because, we're doing parallel, so we're getting more options for our electrons to flow, so resistance should go down. If we are just subtracting them instead of adding them like we are doing in series, well, we would end up with a negative resistance, which is not a thing. That's not real. So how we're going to go about this? Well, if I just first find the opposite of resistance, which is ease, how easy it is for electrons to move. That's just what I'm going to call it. This is not a real thing, but I'm just going to call it ease. So we have the language opposite of it. So how do we do that in math? Well, if we have R, that's our resistance. If we have 1 divided by R, we get our ease. If you want to find some mathematical opposite, you do 1 divided by that thing you want to find the opposite of. Does that make sense? Well, yes. Well, if you have a very high resistance, you have a very low ease, right? So if I'm getting 1 divided by 5,000, well, I'm getting 0.002 or some other zeros. I think that's correct. And if we have a very low resistance, so it's very easy, there's a high ease. So if I have a 0.5 R, we get an ease of 2. So our ease becomes bigger if we get a smaller R. So why does that work? Well, if we are getting 1 over R1 plus 1 over R2, it means we are adding ease together. So eventually we get an amount of ease, an equivalent ease, is the ease of the electrons through this whole circuit. Now, that's useful. We know how easy it can be. So if this is a higher number, it's easier for the electrons to flow. But we don't want to know ease because this ease is not actually a thing. This is a thing I made up. This is a thing I found. It's not real. You can't find it on the internet, I don't think. But this is a way you can rationalize it, if you will. So what we have to do with this ease, well, we have to revert it back to resistance. So how do you get resistance? Again, well, that's 1 over ease again. So we have to do that one thing again. So, this is why I do this again. That's it. If you just if you put this 1 over the thing, if you do the opposite again, you get R. So that's how the equation works. And I think that's elegant. But remember, it's not a real thing. This ease is not actually a thing. But 1 over something is just getting the opposite of, what you were using. It's just a clever way of doing math with a bit more language. It's a concept that makes sense if you think about it long enough.
Now we're able to do some math with multiple resistors, which is useful. Next time, we're going to actually divide voltages, which is also really useful. It starts becoming much more practical once you start dividing voltages and doing stuff. And as always,
Well, I am a licensed physics teacher. This does not make me an expert on the subject. I'm wrong sometimes. Sometimes I know I am, but simplify my explanation at the expense of being completely correct. Sometimes I actually don't know. In either case, I've got a pretty good grasp on the laws of nature and how things work. For the purposes of these videos, the exact correct descriptions of phenomena is not important. I'm trying to give students a new way to look at this world with a technical and logical view. Please feel free to contact me to discuss any of the subject matter within the video.
have a good one. What am I doing with my life?